Today's agenda is to discuss about an algorithm for finding modular exponentiation. That is, we need to find a to the power b modulo n for given integers a and b and a positive integer n. And this algorithm has got many applications in various application domains in computer science. Let us see how we can do modular exponentiation. What is modular exponentiation? As I said, given two non-negative integers a and b and a positive integer n, it is a process of finding a to the power b mod n. For example, given a as 3, b as 4, two non-negative integers, and n as 8. What is a to the power b mod n? Substitute the values of a, b and n. It is 3 to the power 4 mod 8. 3 to the power 4 is 81 mod 8. What is the remainder of dividing 81 with 8? It is 1. So this is what the problem is. Given two non-negative integers a and b, it could be 0. One of they can be 0, and a non-zero natural number or a positive integer, because if the power is 0, nothing to be done, it is 1. We have to find a to the power b mod n. I hope you know about the modular number system from the previous lecture. If you don't know, please go and watch that lecture before you proceed with this. Modular exponentiation is an essential operation in many applications like primality testing, which is a very common process in systems ensuring computer security. So it's a very useful algorithm if we can have one. And before we proceed and see an algorithm for modular exponentiation, let us see what is a loop invariant. Why we need this is because the algorithm that we are going to discuss is going to use loop invariant to prove that what the algorithm is computing is modular exponentiation. Or for understanding what the algorithm is doing, we need to first discuss about loop invariant. A loop looks like this. There is a sequence of instructions in the code. Following that, there is a loop. For the loop, there is a loop control statement. For example, while you have while condition, and this is that condition. Then the loop body. So what is loop invariant? It is a condition I which evaluates to true at the entry to the loop. It is a condition which must be true at the time of the program control coming to the loop control statement for the first time. So at the loop entry it must be true, and it must evaluate to true at the end of the loop body as well. So it must be true when the program control comes to the loop for the first time, and whenever it finishes the loop body at the end, it must be true. So definitely if you go back, it is true. So every time, even the first time and later, whenever the control comes back, the condition must be true. Any such condition is called a loop invariant. So when the loop exits, why the loop exits? The condition must evaluate to false, then only the loop exits. So you know that every time when the control comes to the loop control statement, I is true, and when it comes out, I must be true and the negation of the condition must be true. So I and negation C must be true when the loop exits. I hope you are getting, and this can be used in proving the correctness of an algorithm. We will see an example, loop invariant example, and we will also see how does it help us in proving the functionality or correctness or functional correctness of an algorithm. Here is a pseudocode given, not exactly an algorithm, it is a pseudocode. A function is given foo, which is taking two unsigned values as arguments and doing something. It adds 1 to s and 1 to t in a loop. Can you guess what this algorithm is doing? I hope you guessed something. Later when you apply loop invariant to prove the functionality, you can see what it is doing or whether your guess is correct or not. So here is a loop invariant that I am giving you. I am claiming that for this loop, this is an invariant. This equation is an invariant. S is sum of A and T, and T is always less than or equal to B. So now it is my responsibility to prove that it is a loop invariant. That is, when the control comes to this for the first time, it is true. That is, loop entry, it is true. And whenever you go after this statement, it is true. Loop exit. I can do it. So when the program control comes to it for the first time, what is the value of S? S is A and T is 0. Substitute those values here. You will get this equation. S is A and T is 0. That is why you say S, which is A, is equal to A plus T, T is 0, and T is less than or equal to B. This is the equation. Now you can rewrite it as A is same as A, because plus 0 is this and this equation, and not that B for this is an unsigned integer which is always greater than or equal to 0, and so the equation is true. So we proved that this condition is true at the point of coming to this loop, that is, at loop entry this condition is true. What about the loop exit? Suppose you execute the loop body once, and after that what you are doing in the loop is you are incrementing sy1 and you are incrementing ty1. Now we need to prove that after the loop body this condition is true. We will take each one, say this condition first and then this. We will prove that both are true. And for proving the first part, before executing the loop, we had this part, right? S is equal to A plus T is true. Now what you do in the loop is increment both S and T by 1. Substitute the new values of S and T. You can write it as S plus 1 is equal to A plus T plus 1, which can be easily rewritten as S is equal to A plus T, because if you take 1 to the other side, 1 minus 1 will be cancelled, and so it is S is equal to A plus T, and that is what we want to true actually, that part. Now for the other part, not that before you enter the loop, why you entered the loop body is because the condition is true and the condition is this, no doubt. Now you substitute the new value of T, which is T plus 1 in this condition, so you will get this equation as T plus 1 less than B, because T becomes T plus 1 after the loop body. This can be rewritten as T less than or equal to B. If T plus 1 is less than B, what can be T? T can be less than or equal to B in the new state, right? So this is the new value of T. So you can write it as T plus 1 the new value is less than or equal to B, because in the worst case you have incremented, always you incremented the value of T. So after the loop this is true. So we proved that this is true and this is true, and that I am writing it in a single condition. This is true and this is true. and this is exactly what the loop invariant is. So we proved that at the loop exit as well the condition is true, and hence I is a loop invariant, no doubt. So whenever it comes back it is true, and now when the loop exits, what is true? We saw that the loop invariant and negation of this condition is true. So what is it? The loop invariant is this, and the negation of this condition is t greater than or equal to b. And if you look at this equation, t less than or equal to b and t greater than or equal to b means t is nothing but b. That is the only values of t and b for which these two must be correct. So we are proving that s is equal to a plus t and t is nothing but b. So it tells you that at the end of executing this pseudocode or algorithm, s is nothing but the sum of a b. So what the algorithm is doing is it computes the sum of a and b in the variable s. I hope your guess was correct. So now this is an example which shows what is a loop invariant. It is a condition which is true when the control comes to the loop for the first time, and it is true whenever it comes back to it. And it can be used to prove the functionality of an algorithm or what the algorithm is doing. I hope from this illustrative example you are getting it. For the interest of time, let us proceed and now look at an algorithm for modular exponentiation. I am just copying that algorithm from the textbook. Please don't worry about it. We are going to see what it is doing. So basically the algorithm computes modular exponentiation, which is a to the power b mod n, using repeated squaring. See, here you are finding, and what the result will be in d, and initially it is initialized to 1, and then you are doing squaring repeatedly. After a squaring, if a condition is true, you are also multiplying a with it in the modular system. Okay, we can try to see what it is doing, and to prove that it is finding a to the power b mod n, we will be utilizing a loop invariant, which is not a very simple one, which is a complex one. See that the value of I goes from k to 0. So in this set, it starts from k, it goes all the way down to 0. And take j as the current value of I. It can be any value in this set. The loop invariant first part is telling something. I will tell you what this is using an example. Now see, we have to find a to the power b mod n, and now suppose this is the binary representation of the second argument. Okay, this is the binary representation of the second argument. In this case, I am assuming that the value is 73, and which is represented by this binary string. You can verify it. It is nothing but 2 to the power 3 plus 2 to the power 6. So it is 64 plus 8 plus 1, which is 73. And what is the statement? Now for that to understand, you assume that now the value of I is 2. That is, it started from k, it came down to 2. Suppose it is 2. The value of I is 2. Then this statement claims that c, which is initially 0, c is nothing but the decimal value represented by this part of the binary string is what this statement is telling. The value of c is the decimal value represented by the binary prefix, what bk minus 1, etc., bj plus 1, when the value of j is I is j. Now we are taking the value of I or value of j as 2. So 2 is here. Before 2, what is this prefix? It is 1001. So in this case, we are claiming that c must be 9, which is this binary value, which is 2 to the power 0 plus 2 to the power 3. So if it starts at here, it is the 0th position, first position, second, third. Okay, this is what the first part of the loop invariant is claiming. We will prove that it is a loop invariant. and the second part of the loop invariant says d which is initialized to 1 is nothing but a to the power c modulo n. We will prove it. Now when I is equal to k, that means when the program control comes to the loop for the first time, right, then I is equal to k, that is the initialization. We have to prove that the loop invariant both are correct, and at this time you know that c is nothing but 0, and which is true. What you are saying is c is the decimal value represented by the binary prefix, because the value of I is k, the prefix is null string. I hope you remember what that prefix is. If k is standing somewhere here, this is the prefix. If k is here itself, or I is standing at k itself, the prefix is null string. So null string can represent only 0. So that is correct. Now what about the value of d? D is we have to prove that it is a to the power c mod n, but c is 0. So what is it? A to the power 0 mod n. Regardless of the value of a to the power 0 is 1. 1 modulo n for a positive integer n is always 1, and which is correct because now you know that for the first time d is initialized to 1. So this is exactly what a to the power c mod n is. So at the loop entry we are proving that our condition is correct. Now we also have to prove that at loop exit it is correct. So after the loop, it depends on what it do is depending on whether the value, the next bit here is a 1 or 0, right. Now you consider the case where the next bit that you are getting from here is 0. Then no doubt the if part will not be executed. If bi is 0, this will not be executed. So what you are doing inside the loop body is you are taking c as 2c and d as d square mod n. Okay, and if you know about binary string, the first part is very clear, because you are doing c, you are making it to 2c. Okay, and suppose this was the case. Originally the value of c when I is equal to 2 is 9, that is what we found. Now when you go to the next bit, what is it? It is 0. You know that when you do a left shift and the next value is 0, the value represented by that binary string will be doubled. This is exactly what we are saying. In this case, previously it was 9, you will be doubling it, it is 18, and 18 can be verified as the binary, the decimal value represented by this binary string, and that is always true, because if you left shift and if the next bit that you are getting here is a 0, then the value represented is doubled. So we proved the first part. Okay, we are doubling it. Now the second part, and you are computing d as d square mod n, and from the loop invariant you know that when you came inside, d is nothing but a to the power c mod n. So you substitute the value of d as a to the power c. So this is what you are getting, and you know that a to the power c, the whole square is nothing but a to the power 2c. So it is of the form, the new value of d is a to the power 2c mod n, and that is exactly the new value of c. So you are getting it as the new value of d as a to the power the new value of c mod n, and that is what you wanted to prove. See that this is what you wanted to prove. The new value of d is nothing but a to the power the new value of c, which is 2c mod n. So we proved that in that case when bi equal to 0, both these conditions be proved. Now you consider the other case where bi is 1, then what you are doing is c becomes 2c first and then c is incremented. So 2c plus 1, it is doubled and then incremented. No need to explain, you know that this is an example case where previously I was 3 and then this value represented was 4. Then in the new case we are claiming that it will be 2 into c plus 1. 2 into 4 plus 1 is 9, and which is exactly the value represented by the binary string when you take the next bit as well. And this is a very well known result. If you left shift a binary string and put a 1 in this position, then the new value will be twice the value existed plus 1. That is what you know, and you are verifying it. I hope you are getting, otherwise please watch it again and verify that what we are telling is correct. Now we need to, it remains to prove that in that case as well, the new value of d will be a to the power the new value of c modulo n. The new value of c is 2c plus 1. So we have to prove that the new value of d is a to the power 2c plus 1 mod n. We can try what you are getting. So what you are doing inside the loop is, first you compute d as d square mod n, d square, and then to that value you are multiplying a. So it's actually d square multiplied by a mod n. And what is it? From the loop invariant, you know that when you came to the loop, what was a? Sorry, what was d? D was a to the power c mod n. So you substitute the value of d as a to the power c, you will get this equation, and a to the power c the whole square is nothing but a to the power 2c multiplied by a, that is a to the power 2c plus 1. This is exactly what we wanted to prove. The new value of d is a to the power 2c plus 1, that is the new value of c. So we are proving that the new value of d is a to the power the new value of c modulo n. So we are proving that it is also true at the exit from the loop. So we have proved both the cases, and hence this is the loop invariant. Now we can try to utilize this to prove that the algorithm is computing exactly the modular exponentiation. When the loop exit, what must be true? I must be minus 1, because I should vary from k to 0. So when I becomes minus 1, the loop exits. So I becomes minus 1. So what can be the value of c? From the loop invariant, we know that it must be represented by the entire binary string, which is exactly the value of b, because I came to minus 1. Now the prefix is the entire binary string representing the value of b. So c is nothing but b. And now what this is telling you is d is nothing but a to the power c mod n. Now we proved that c is nothing but b. So we are proving that at the end, when the loop exit, d, which is the value returned, is nothing but a to the power b modulo n. And this is exactly what we wanted to compute. So using a sufficient loop invariant, we proved that what is returned is a to the power b mod n. And not that we proved the correctness of the loop invariant. When the controller came to the loop body for the first time, it was true, and whenever it returned, it was true. With this, we are coming to the end of this lecture, and I am giving you an exercise problem for you to apply this algorithm on these values: a as 6, b as 593, and n as 511. You just apply the algorithm and see how this algorithm is working. With this, we are finishing this lecture. So today we looked at an algorithm for modular exponentiation. We are computing a to the power b modulo n, and we also have learned about loop invariants, which is a condition which is true when the program controller comes to the loop for the first time, and also at the point of exit from the loop. That is immediately after executing the last statement in the loop body, it must be true. So, if I is the loop invariant, we can see that I is true every time when the program control comes to the loop control statement. It may be for the first time or just after executing the loop body. Thank you.